So in this lesson, we're going to look a little bit at endothermic and exothermic reactions. And so to understand how these work, we have to think a little bit about chemical reactions. And so, in chemical reactions, we start off with certain compounds. And so, we've done this reaction where we've said, like making water right here. And so we do like hydrogen plus oxygen, and then we had to balance it out. And so to balance it out, we had to put, let's see, a 2 here to get those right, and then a 2 right here, and that balances the equation. But, to do this reaction, what we've got to do is we've got to take this H2 right here, and that's 2 hydrogen atoms that are bonded together. We have to break those bonds apart first. And then we have to take this O2, that's 2 oxygen atoms bonded together, and we have to break those 2 bonds apart. And so we break apart the atoms that are in the reactants here. We break those bonds, and then once we've done that, we have the free atoms, and then we form the new bonds that are in the H2O. And so anytime you have a chemical reaction, you have breaking of the old bonds to separate the atoms, then making the new bonds to create the new substances here. And the reason why this is important is that this idea of breaking bonds and then making bonds is going to help us to understand why it is that certain chemical reactions either release energy, they produce heat whenever the chemical reaction goes on, or they absorb heat and they cool down their surroundings here. And so the reason why this happens is because whenever these original bonds are broken, those original bonds have a certain amount of chemical energy. And so let's imagine that we have, some reactants here, we have some products here, and let's look at sort of the energy has. So one, the reactants may have a chemical energy that's like this, but then once those bonds are broken, once the new bonds are formed in the new products may have only a chemical energy that's only this much right here. And so there's a change in the amount of chemical energy, or the amount of bond energy in the reactants versus the products. Now, the reason why this is going to be important is, as it says here, energy is conserved in a closed system. Remember, we said that energy cannot be created, it cannot be destroyed, but it can change forms. And so what will happen here is, for this reactant and for this product, is the total energy will stay the same, which means that the energy that started off here, that ends up here, that starts off with the reactants and ends in the products here, that energy can't be destroyed, but it can change. And so let's imagine this. Let's say that green line is our total amount of energy that we have. And so initially is that the remainder of that energy that's in here is going to basically be thermal energy. It's going to be energy of heat, versus, as we said before, is that the red here is going to be the chemical energy that's in the bonds. Well, whenever the new bonds form, since the total energy can't go away, it doesn't change because it's a closed system right here, then that thermal energy will have to have gone up, because the chemical energy went down, because the total of thermal and chemical has to stay the same. So when the chemical energy drops, as it goes from the chemical energy in the original reactants to the chemical energy in the products, is that energy has to go into thermal energy. And so for that particular reaction, since the thermal energy went up, that means it's going to release heat, and so the substance will get hotter. Now, if this had reversed, if it had started off with a lower chemical energy for the bonds of the reactants and went to a higher chemical energy for the bonds of the products, then that would mean the thermal energy would have had to have decreased, and so it would have gotten colder. So 2 terms that we use for these 2 types of reactions. One where the chemical energy drops, and so the thermal energy goes up, and the other where the chemical energy goes up, which means the thermal energy goes down. So the terms that we use for these are called exothermic reactions and endothermic reactions. So an exothermic reaction is basically a reaction where energy is released in the form of heat. And so if you were to stick your hand into a reaction between 2 things that was exothermic, you would feel your hand getting warmer, because what's happening is that the total chemical energy in the bonds of the reactants is bigger than the total chemical energy of the products. And so since the chemical energy drops, that energy has to go somewhere, and so instead that energy goes into thermal energy. So the thermal energy goes up and it releases heat. And so if you want to know if you have a thermal reaction that's exothermic, then you say, is it getting hotter? If it's getting hotter, then that means it's exothermic here. So very common example of an exothermic reaction, got it right here, fire. Fire obviously produces a lot of heat, it's a chemical reaction, and so the reason why is because if we were to look at the chemical energy of, in this case, the wax that's burning right in here, look at the chemical energy of that, compare it with the chemical energy of the products that are made out of this, the carbon dioxide and the water, which are going to go up into the air as this burns, is that we would find out that the chemical energy of the wax is higher than the chemical energy of the products, the carbon dioxide and the water. And so because the chemical energy has dropped, that means the thermal energy must have increased. So next possibility is what's called an endothermic reaction. And so in an endothermic reaction, what's happening is the heat energy is absorbed from the reacting substances. If you stuck your hand into or felt a container that contained an endothermic reaction, you would find that it feels cold, because what's happening is that the chemical energy is increasing. So in an endothermic reaction, you start off with a low chemical energy for your reactants, and then you end up with a higher chemical energy with your products. So because of the fact that the chemical energy had to increase, that would mean that the thermal energy would have to decrease. And so we may have started off with a large amount of thermal energy. We're going to end up with only a very small amount of thermal energy. And so the thermal energy dropped, and so therefore it felt like it's getting cooler in terms of doing that. So examples of endothermic reactions, there aren't a whole lot of them, not compared with exothermic. There are a lot of exothermic reactions, not a huge number of endothermic reactions. But cold packs, so the ones that sometimes you break and you put on, say if you've got a sore muscle or something like that, that would be an example of an endothermic reaction. Another one is sort of the classic elementary school. If you mix vinegar and baking soda to make sort of that volcano, is that reaction is actually slightly endothermic. Is if you stick a thermometer in it, you'll find that it gets a little bit cooler whenever that happens. And so these are some examples of exothermic reactions and endothermic. Exothermic reactions give off heat because the chemical energy has dropped, and so that means that the thermal energy has risen. Endothermic reactions tend to absorb heat, so that you feel them, they feel cool, because the fact that the chemical energy has risen, which means the thermal energy has to drop. So let's look a little more in detail at the energy that's in these chemical bonds. So we said that chemical energy is a type of potential energy. We discussed that at the very beginning of the year, where we looked at different types of potential energies. And one of the ways that, one of the things that we learned about potential energies is that for objects that are free to move, they typically want to lower their potential energy. And so when atoms bond, they do this lowering by trying to trade or share or give or take electrons to end up with that full outermost energy level of electrons. Either if they have a high electronegativity of taking electrons, they're electron acceptors, so they end up with that full set of 8 outermost energy level electrons, or if they're donors, they give those away. And so when they do that, they manage to lower their potential energy, they lower their chemical energy. And so we have a graph that's down here at the bottom. This one may be familiar to you, is that we have on the y-axis the amount of chemical energy increasing as we go up. On the x-axis we have the distance between the two atoms. So you can see these two atoms are very close together. These are a little farther away still, and even the farthest away. And then the red line that's down here indicates basically the chemical energy. So you can see the chemical energy whenever the atoms are far apart starts off high. As they get closer, the chemical energy drops. It reaches a minimum, and then it starts rising again. And so because the fact that whenever atoms bond, they want to reach their lowest potential energy, they're going to end up being at a distance around here. So the distance between this spot over there is going to be the length of that chemical bond. And so when they're bonded together, so we'll say we start off with some reactants, they're all bonded together, they have this really low chemical energy right here. And so in order to do a chemical reaction, we said the first thing we have to do is we have to break those bonds, we have to pull those bonds apart. And so when we do that and separate those atoms, they are going to move outward, and when they move outward, their chemical energy is going to increase. And so the process of breaking chemical bonds results in an increase in chemical energy. And so we break those bonds apart, the chemical energy goes up. But then when we make new bonds, what's going to happen is that now our new atoms are going to get closer together, and so as they get closer together going here, the chemical energy is going to go back down again. Now, unless you're reforming the same bonds, it's probably not going to go down to the same spot. what may happen is that for our first cases, it's down here, but then when they form new bonds, maybe those new bonds, the little curve looks like this, and so instead of going all the way down to here, they just go down to this spot right here. And so if that were the case, that we break apart the bonds out here and then we make new bonds coming down here, that we would have a higher chemical energy at the end than the chemical energy at the beginning. So the chemical energy of the reactants was lower, the chemical energy of the products was higher. And so that's basically what happens whenever we break apart chemical bonds. That's what happens to the chemical energy. We go through this process where we separate the atoms apart, the chemical energy rises, and then we put them back together and then form new bonds, and the chemical energy drops again. So if we look at this as all one piece, we have sort of this diagram over here, and so we start off with our reactants. They have a certain chemical energy down here, and so whenever we start this off, we have our reactants. Their atoms start at a relatively low chemical energy, and they have that low chemical energy because they're at that lowest energy because they're most stable there. They're shared electrons, they have that full outermost energy level. But to react them, we have to pull those atoms apart. And so step 2, the atoms' bonds are broken. When that happens, we have to move the atoms apart, and that moves them to a higher chemical energy, and so that chemical energy is going to rise until they're all broken apart. And when they're all broken apart, they're in what's called the activated complex. What we're going to see is that activated complex atoms are basically a mixture of loose atoms. It's partially formed molecules. Ones that what have happened is that the molecules are in the process of being taken apart, their bonds are being broken, or new molecules are in the process of being formed, so they're not fully formed yet. You may even have some temporary molecules that may form briefly, that atoms bond together, then break apart again. But basically it's a sort of mixture of partially broken apart molecules that you have here. And that's the point where basically you're going to reach the highest chemical energy. But now we have to form our new bonds. So step 3 is the new bonds between the atoms are formed. And when those new bonds formed, the chemical energy is going to drop again, and so it's going to reach its new spot here. So this is sort of the steps that happen to the bond energy in the process of a chemical reaction. In the reactants, they start off bonded together. They're at a fairly low chemical energy. We have to spread them apart, and we spread them apart, the chemical energy rises, and then we start putting the bonds together again, and when it forms new bonds, that chemical energy is going to drop again because it wants to reach that lowest possible potential energy that it can. Taking a look at this. This picture that we just did here on the right, is this an exothermic or endothermic reaction? Well, in order to determine that, what we want to do is we want to look at what happens to the chemical energy. The chemical energy started off right here, right? It ended with not nearly as much chemical energy. Now, we know that the thermal energy, the total energy has to stay the same. And so if we say the total energy is up here, this would start off with this much thermal energy right here, and it would end with this much thermal energy, because that energy can't be created or destroyed. It only changes form from chemical into thermal. So you can see the thermal energy started off this size, but ended up with much more thermal energy, and so that would mean this would be an exothermic reaction, because the chemical energy dropped, which would mean that the thermal energy rose if it's a closed system, and we're going to assume that all our systems here are closed unless you're told otherwise. So we could also look at this in terms of this particular energy diagram. This is a reaction showing that same one we talked about at the beginning. We have 2H2 plus O2 yields 2H2O. And so we start off with 2 H2s and 1 O2. And so you can see our H2s right here. We have 2 hydrogens that are bonded together. Then we have underneath that the same thing, 2 hydrogens that are bonded together right here. We've got those. And then we can have our 2 oxygens that are bonded together right here. And so the first step that has to happen, we have to break those bonds. And so you can see that now over on the second side here, we're in the activated complex that's right here. And so in that activated complex, you can see the molecules have all been, or the atoms have all been broken apart. And then the last step is then that we form H2O. We have 2 H2Os. We have the oxygens in the middle. They bond to the 2 hydrogens right here. The oxygen bonds to the 2 hydrogens to make 2 water molecules because it's 2 H2O. If we look at the chemical energy, though, you could see in the original situation, we've got this chemical energy that it's showing in the green down here. It's about that high. That's about how much chemical energy we have. When we break them apart, you can see the chemical energy has risen to a higher amount when they're in the activated complex, so we had to pull those bonds apart. And then when it formed the water molecules, at the end, the chemical energy is back low again. And so the chemical energy overall dropped. Even though it went up at first, it ended up dropping when we compared the reactants versus the products. And so that would mean that in this case, this is going to be an exothermic reaction, because you can see from the blue here, it listed as heat and light energy, but this is really just thermal energy. That thermal energy went from being relatively small to being much, much larger. So this would be an exothermic reaction. So, all right, so here's the next question then. What would an endothermic reaction look like? So this particular reaction, whenever you react hydrogen and oxygen, is you light them on fire to do this to produce water. It's very exothermic. But if it was endothermic, how would it look differently? Well, an endothermic reaction would mean that the energy of the final substances, that is, of our products, should be higher than the energy of the reactants. And so instead of being this little one right here, it should be a higher amount. Now, how high though? Well, let's try it right here. Just because I have it drawn up there, we'll draw this out. Let's say this is where our new chemical energy is going to be. And so let's draw our little diagram. We start off with our reactants energy right here. We separate them apart, which gives us our activated complex, has a higher energy here. But now what's going to happen is the energy is going to drop right here. And so we have a situation like this. As you can see, is from the blue, which is our thermal energy. The thermal energy started off relatively large. It got really tiny in the activated complex. It got a little larger again when we got to the end, but you can still see that the thermal energy at the beginning for the reactants is larger than the thermal energy of the products. This would be an endothermic reaction. Well, could we have an even bigger endothermic reaction? What if, instead of doing what we just did right there, what if we did this? Let's just make the whole thing. Can we make the whole thing chemical energy at the end where it has no thermal energy? Well, the answer is no. And the reason why is that for this to happen, we would have to basically separate the molecules apart, and that puts them in the activated complex right here, and would have to go up even farther. And that's not something that we can do, because the only reason why it wants to go from these separated atoms into the molecules is it wants to lower its potential energy. If the molecules had a higher potential energy than the activated complex, they would never do that. They would never go apart, because remember, they want to reach a lower energy, not a higher energy. And so it's not possible to have an energy raise up after the activated complex. It always has to be at least a little bit lower, and it doesn't have to be much lower. You could have a situation where it just goes down just a tiny, tiny bit, and that would be okay. That would be a very, very endothermic reaction. But you can't have a situation where it either starts with a higher energy than the activated complex, and you can't have a situation where it ends with a higher energy in the activated complex. Both those two situations are not possible, but having it even drop just a little bit is quite okay in terms of that. So let's look at the standard. The standard says that we need to develop a model to illustrate that the release or absorption of energy from a chemical reaction depends upon the changes in total bond energy. So our goal here is going to be looking at our action verb. Our action verb is develop, right? And so we are going to be developing what? It says that we are developing a model. And so as we talked about earlier, models are basically things that we use in science to help us to understand or help us to explain some phenomenon. And so those models can be physical models you build, they could be mathematical models, they could be graphical models, they could be the diagrams. You can use any one of these. But our goal is to show, to illustrate, that the release or absorption of energy, and so release or absorption of energy is another sort of way of saying if it releases energy, then it's going to be an exothermic. If it absorbs energy, then it's going to be an endothermic reaction. And so that's what we're saying here, is that to show that if the reaction is exothermic or endothermic depends on what? The changes in total bond energy. Well, bond energy is, as we said, just another fancy term for chemical energy. And so we need to show that if we looked at the reactants and we looked at the products, that we could show using a model that the bond energy, the chemical energy as it changes, that we could explain whether or not a reaction is exothermic or endothermic, or show what happens in an exothermic or an endothermic reaction to the bond energy. And so this is what we're going to do for our standard. So to meet this standard, we want to show that in all cases the amount of energy released or absorbed in a reaction, that is that heat energy that's produced, the thermal energy that's released or absorbed, is determined by the changes in the chemical energy between the reactants and products. And so what I want you to do is I want you to start working on this model with any time that you have left to do in ILT until we meet again. And so your model needs to show how that both a release of energy, that is an exothermic reaction, and an absorption of energy, that is an endothermic reaction, can be explained using those bond energies. It also needs to show how that the amount of energy released is determined by the changes in bond energy. So really that means that your model needs to show 4 different situations. It needs to show a situation that is basically very exothermic. It needs to show a situation that is slightly exothermic. And it needs to show a situation that is very endothermic and a situation that is slightly endothermic, if I can write out here. And so you'll want to show what happens to the bond energies in each of these 4 situations. And so by showing it in these 4 situations, then if you create models that do this, then you should be good to go. And so we're going to be working on this, as I said, in ILT here. We're going to be working on this moving forward in our classes for the remainder of the week. And this is going to be our assessment. And so once you've finished this, you can do this on paper, you can do this on computer. You'll want to, or once you've got at least one of these 4 done, go ahead and show it to me so that way I can see it, and you'll be able to do that once I get back again. So that is what our next step is. Once you've gone through the video here, then go ahead and start working on your models. You'll do these individually. These are not done in groups, and that's what our plan is.